Hello, and welcome back to the course. So we're going to look at isolated singularities and how they relate to the Laurent series. So this is subsection 5.2.2 in the book. So let's start with some examples, right? So 1 over z, that is an isolated singularity at z equals 0. It is a pole of order 1, right? Now, if you look at the Laurent series of this, well, that's just the 1 over z, right? I mean, that is the Laurent series. All the terms are 0 except the negative first one, right? The first the first negative term, the one corresponding to the negative first power of z, right? Because that's what it is, right? So that's just its Laurent series, right? Now, the thing that we notice here is that it's a pole of order 1, and all the coefficients of order less than -1 are 0, right? So all the coefficients of negative order, less than -1, right? So there's only one of these negative order terms. All the other ones are 0, right? And it's of order -1, and that 1 is the order of the pole. Okay, let's make it slightly more complicated. Let's just add in some. This is not really changing anything, except it is making it's making it look more like a series, basically. So if I add in all these powers, all the positive powers, right? So I really start. It's almost like a geometric series, but I start at -1 instead of at 0. Right. Now it's still a pole of order 1 at the origin, right? And still, I have all the coefficients in the series of order less than -1 are 0, right? It's the same idea. Just looks more like a Laurent series, right? Okay, I could make it even a little bit more complicated. Let's start at -3, right? So I just have, I have this Laurent series, right? And it starts at -3, right? This is the pole of order 3 because of this guy, right? And again, all the coefficients of order less than -3 are 0, right? Finally, another example, an essential singularity. What if I stick in all the negative terms? Well, so let's look at e to the minus. Oh, e to the 1 over z, not -1. E to the 1 over z. So I just plug that in, and I get this Laurent series, and that is an essential singularity at z equals 0. We saw that, and this series, all actually all of the negative orders have non-zero coefficients, but particularly infinitely many, right? And that's actually something that happens. Like these examples are basically giving you, how essentially all singularities work with respect to the Laurent series. So here's the general statement. It's not hard to prove. The proof is an exercise. So suppose that you have a holomorphic function with an isolated singularity at P, right? So we're defining it on some little disk, little punctured disk, right? And we write down the corresponding Laurent series. You compute the Laurent series. Then the singularity is removable if and only if the negative coefficients, the CNs for -n, are all 0, right? In which case, this Laurent series, well, I mean, it's a power series, right? It starts at n equals 0, right? So that's what you think it should be, right? So that's what it means to be. Well, that's what this proposition says is an equivalent thing to being removable. You can compute the Laurent series, and if all the negative order terms are 0, then it's removable. If most of them, all but finitely many, are 0, then we have a pole. We have the singularity, the pole of order k, precisely k, if and only if, well, all the terms Cn for n less than negative k, right? So beyond negative k, we just get zeros. And since we want it to be exactly of order k, then we're saying that it should have the negative kth term should be non-zero, right? So C negative k should be non-zero. All the lower lower order terms should be 0. That's an if and only if for this being a pole of order k. And basically, the only other possibility is that it's an essential singularity, and that just means that Cn is non-zero for infinitely many negative n, right? So that's basically when number 2 is not true, right, and number 1 is not true, right? And that's that will give you an if and only if for essential, right? So you can if you have the Laurent series, you can decide on the type of the singularity, and I guess vice versa. If you know the type of the singularity, you know how the Laurent series will sort of look, right? So either it starts at some non-negative n, in which case it's removable, or it starts at some finite but negative n, in which case it's a pole, or you have to start at minus infinity, in which case it's essential. All right, and the proof is an exercise. It's not too hard. It's what we did last time. Really, the thing is the uniqueness of the Laurent series is the key point here, and then doing what we did last time. All right, now the negative part has a name. It's usually called the principal part. So this is if I take a look at an isolated singularity, so a holomorphic function with an isolated singularity, and compute the Laurent series around that point, then all the negative terms, that's what we call the principal part, right? And it's just maybe an observation, right? I mean, if you knew the principal part, right, if you subtract it from f, then that has a removable singularity, right? Which you could sort of think of that's what the principal part is, right? All right. Now, let's look at e to the 1 over z and relate it to e to the z, right? So 1 over z takes infinity to 0 and 0 to infinity, right? So we can talk about singularity and infinity. Let's do it for an entire function. You can really do it for non-entire function, just as long as it's defined in a punctured neighborhood of infinity. So given this f, right? So it's not defined at infinity, but it has an isolated singularity at infinity. So let's just stick with entire functions for here. So now C is a subset of the Riemann sphere, C infinity, right? And 1 over z, that's a self-mapping of the Riemann sphere that just flips 0 and infinity, right? So if I take a look at f, and instead of looking at f of z, I look at f of 1 over z, well, really, when z is near 0, then 1 over z is near infinity, right? So really, that function has an isolated singularity at 0, right? And I just think of that as the singularity of f at infinity, right? So e to the z, for example, looking at this example, e to the z has an essential singularity at infinity because e to the 1 over z has an essential singularity at 0, right? So that's what I mean by it having an essential singularity at infinity, right? But we have all the other types of singularities as well, right? All right. So let's just look at some useful exercises. So the first exercise, that sort of just follows from the, or you can prove it using the proposition that we just, didn't prove. That was an exercise. That, if I take something with a pole and something with an essential singularity, the essential singularity wins out. It has to have an essential singularity. You cannot cancel out an essential singularity. Now, you can cancel out an essential singularity with an essential singularity, right? Because you can just cancel the function, right? But if you have, you cannot cancel it out with a pole, right? All right. Now, this e to the 1 over z, it's a somewhat more general concept, or somewhat more general idea, is that if you have a pole and you take the exponential of that, you actually get always an essential singularity, right? So do this for a simple pole first, and see what happens. All right. So now another sort of interesting thing about singularities at infinity is that it sort of tells us what polynomials are, and kind of tells us the difference between e to the z. So e to the z has an essential singularity at infinity, and kind of pole. Well, I mean, e to the z has terms of all orders. That's sort of the idea. But a polynomial is something that only has terms of up to a finite order, up to a finite degree, right? And that's actually, that degree is the order of the pole at infinity of this function. And so a function, an entire holomorphic function, is a polynomial if and only if it has a pole at infinity, and the order of the pole is actually a degree of this polynomial. And that's basically, a version of what we just, like of the proposition, right? Just flipping the 1 over z, right? All right, now another useful exercise that follows from this, and actually sort of related to the previous one, is an automorphism, right? So if you have an automorphism of C, right? So something that's a biholomorphic map of C to C, right? Then it's actually this affine function, right? So there's some constants A and B, and the function is AZ plus B, right? That's the only thing that you can do. The only automorphisms of C are that, right? And basically, what you want, the way that you want to show that that's what it is to show that you have a simple pole at infinity. First show that it's a pole, then show that it's simple. Yeah, right. So, all right. So that's it for today. Or for this lecture. And next time, what we're going to look at is, a little bit more at the, how essential singularities are sort of wild, or the functions near their essential singularities are wild. We're going to prove sort of a baby version of Picard's term, the sort of so-called Cassarati-Weierstrass term. The reason why we prove that is because it's simple to prove. Picard's theorem is hard to prove, but it already tells you how bad essential singularities are, or how nice. I don't know. Depends on your point of view, right? But how wild the functions are near an essential singularity. So the functions are fairly tame near a pole or a removable singularity. All right. So see you then.